Alright, now I'm going to do problem 43, chapter 10. In problem 43, it says you have been hired to design a spring-launched roller coaster that will carry 2 passengers per car. The car goes up a 10-meter high hill, then descends 15 meters to the track's lowest point. Alright, so before we go any further, let's draw it. So you have a car right here that can hold 2 passengers. It's going to go up a hill, and it's going to come back down to a lower hill. If I consider this a starting point, it goes up to 10 meters, but then from that point, it descends 15 meters to the lowest point down here. Okay? And you launch this car by putting a spring here. So there's a spring that's going to launch the car. And the spring can be compressed 2 meters. And that the loaded car will have a maximum, so the mass of the car is 400 kilograms. Alright, for safety reasons, the spring constant should be 10% larger than the minimum. So whatever we're going to solve for what K we need, and then we're going to add 10% to that to make sure that we get it strong enough, the spring strong enough. And so part A, what they're asking is what spring constant do we need? Alright, so when we do this, to figure out what spring constant is necessary, we have to look at the situation and say, okay, so what this car has to do, this car has to get up to the top of the hill. Once it gets over the top of the hill, then gravity will take over and it'll just go off. So all we have to do is get the car to the top of the hill. That spring constant, that's the job of the spring, is get the car to the top of the hill. After that, it's just a gravity situation. So we're going to do an energy initial equals energy final. And the energy initial, again, is going to be 1/2 kx squared. Because we're going to call our gravitational potential equal to 0 at this point right here. Okay? At the starting point. So that's all it has. There's no initial velocity, there's no gravitational potential. Now the final, when it gets to the top of the hill right here, we want it to just get to the top of the hill. We want to know how strong the spring is to get it to the top of the hill. Then we're going to add 10%, so we'll make sure that it gets over the hill. But first we want to figure out what the spring constant is necessary to get it to the top of the hill. So at the top of the hill, it'll have no velocity, but it will have gravitational potential. And this is H here, H1, we'll call it. That's all you got because there's no velocity at that point, no other energy. So we're just going to solve this. We're going to solve this for K. So K is going to be equal to 2 mgh over x squared. So when we solve it for K, we get this as 2 times 400 times 9.8 times 10 all over 2 squared. And when you solve for that, you get 19,600 newtons per meter. Now we add 10%, or we're going to say that K is equal to K plus 10% of K, which is going to be equal to 19,600 plus 1,960, which gives you 21,560 newtons per meter. That is the answer to part A. That is the spring constant we need. By adding that 10%, then we guarantee that every single time you launch it, it will make it over the top with a little bit of speed. There's going to be extra energy there. We don't want a car to go up and then fall back down. All right, part B then asks, well, what's the maximum speed? Well, the maximum speed is going to occur when it's down here at the bottom of the valley. So what we want is the velocity here, the velocity at this point. So, back to energy initial equals energy final. The energy initial is still just spring energy. But now we also have to look and say, oh, where's it at? Well, we're calling this our 0 here, so it's going downhill, right? So it's actually has energy to begin with. It started up here. We don't care about this hill in between, does not matter now. Energy doesn't care what happens in between. All we care about is the initial point and the final point. So it also has gravitational potential because it's uphill. But it's uphill by this amount here. We're going to call this H2. So when it starts, it's that much higher than its finished position. And when it gets down to here, it's all going to be just kinetic energy because it only has velocity. No gravitational potential, no spring going on, and there's no friction. So this is our equation. Now the tricky thing here was making sure you put the gravitational potential on the right side of the equation. Remember, we're starting uphill going down, you put it on the initial side. If you're going the other way, you put it on the final side. That's why it was on the final side here, the initial side here. And then we're going to solve this for the velocity. First I'm going to multiply it through by 2, so this becomes 2mg h2 plus kx squared is equal to mv squared. Then I'm going to divide by m and take the square root. So I'm going to say, oh, this is equal to 2mg h2 plus kx squared all over m. Square root of all that is my velocity. And so I know all that, so this is going to be the square root of 2 times 400 times 9.8 times 5. Notice 5 is the distance here because we went, this is 5 below. The total is 15. Plus 21,560 times 2 squared all over the mass of 400. You do all that, you get a velocity of 18.6 meters per second, or 2 sig figs, 19 meters per second. There you go. That's how you do number 43. All right, let's do number 46. I think I can do it on the same one here. So problem 46, in problem 46 it states a 1,000 kilogram safe, so this is 1,000 kilogram safe, which is a metric ton, by the way, is 2 meters above, so this is 2 meters above, a heavy duty spring. Has to be a very heavy duty spring. When the rope holding the safe breaks, so there was a rope holding it, the rope breaks. Okay. The safe hits the spring and compresses it 50 centimeters. What is the spring constant? So we want to try to figure out what K is. Question. Okay. So up here, so we have energy initial. This is number 46, by the way. Energy initial equals energy final. Well, energy initial is how high it is. So how high it is going to be mgh. And when it falls all the way down, it's going to compress the spring. And so at the bottom here, this bottom point, after the spring is compressed, we're going to call that our gravitational potential equal to 0 at that point. This is equal to energy final. All that energy goes to compress the spring. So you're taking gravitational potential, you're converting it to spring potential energy. Okay? Now, what we want to do is solve this for K. So K is just equal to 2mgh over x squared. Or K is equal to 2 times 1,000 times 9.8. Now we have to do h, but we got to be careful. H is 2 meters above the spring, but the spring actually compresses all the way down here to 50 centimeters, so it's actually 2.5 meters, 2.5, those have to add together to the point where it compresses the spring. You can't just go from here to where it touches the spring, you have to go all the way till the spring is compressed. And then the amount of the spring compression is 0.5 meters squared. When you solve for that, you get that K is equal to 196,000 newtons per meter. And that's the answer. All right. Pretty easy one. The thing you had to be careful was to make sure you got your height right. It wasn't 2 meters, it's actually 2.5 meters.